Hey, welcome to this explainer. Today, we're going to pull back the curtain on an invisible force that literally shapes everything you hear. Think of it as a hidden architect living inside your own body.
So let me ask you this. What if I told you that sound gets twisted, amplified, and sometimes completely canceled out inside your ear canal before it even has a chance to reach your eardrum?
Because believe it or not, that's exactly what's going on. And it's all thanks to something we can call phantom waves.
Now, these aren't science fiction. They are very real physical phenomena, and they are shaping how you hear the world this very second. To really get how this works, we need to start with one single core principle. Okay, let's dive into this.
All right, to get a handle on these phantom waves, we first have to talk about a basic idea from physics, resonance. You can think of it as the reason why every single object out there, from a tiny wine glass to a massive bridge, has a favorite sound it just loves to make.
So what even is resonance? Well, put simply, it's just the natural frequency at which an object prefers to vibrate. You know when you push someone on a swing? You naturally push at its resonant frequency to get it to go higher and higher with the least effort. Well, the exact same idea applies to sound waves and objects.
And musical instruments are the perfect example of this. A small violin with its short, tight strings, it's going to naturally resonate at higher frequencies. But a big old bass with its long, heavy strings, that's going to resonate at lower frequencies. The physical makeup of an object basically decides what its favorite musical note is.
So how does this all lead to our so-called phantom waves? Well, when a wave moves through something, say a guitar string or even just the air inside a tube, and it hits a dead end, something really amazing happens. This is the moment a standing wave is born. It's really just a simple four-step process. First, you have a wave traveling along. Second, it hits an obstacle and reflects back on itself, kind of like an echo. Third, and this is the key part, that reflected wave starts to interact and interfere with all the new waves that are still coming in. And when the frequency is just right at the object's resonant frequency, they just lock into this perfect stable pattern, the standing wave. It looks like it's standing perfectly still, but it is actually a whirlwind of energy. And this motionless pattern? It has two super important parts. You've got places where the reflected wave perfectly cancels out the incoming wave. We call these nodes. They're points of absolute zero movement. That's destructive interference. But then you have spots where the waves add their energy together, creating antinodes, points of maximum vibration, maximum amplification. That's constructive interference. These are the acoustic hotspots and dead spots we're talking about.
So now for the big payoff. What in the world does any of this have to do with audiology? Well, everything. Because your ear canal, it's not just some simple tube. It's actually a finely tuned musical instrument designed by evolution to resonate.
Okay, so in physics, we usually talk about two basic kinds of tube resonators. You've got your half-wave resonator, which is open at both ends, think of a flute. And then you've got the quarter-wave resonator, open at one end but closed at the other, kind of like when you blow across the top of a bottle. Just pay attention to the key differences here, like where the nodes and antinodes pop up and the harmonics they create. So take a look. Which one of these do you think is a dead ringer for the structure of your own ear? A tube that's open on both ends, or one that's closed off on one side?
Yep, you got it. It's the quarter-wave resonator. Your ear canal is open to the world, of course, but at the other end, it's sealed off by your eardrum. And that very specific shape means it is physically perfectly designed to create standing waves. And the result of this whole design is just fascinating. The average adult ear canal has a main resonant frequency right around 3,000 Hz. This means our ears naturally, physically crank up the volume on sounds in this exact range. And why does that matter? Well, that range is absolutely critical for understanding the consonants in human speech. It's like we all have a built-in amplifier just for communication.
But, and there's always a but, this amazing natural phenomenon has a bit of a dark side, especially when you get into a clinical setting. What works perfectly inside our heads can actually create a serious acoustic trap when we're trying to do accurate hearing tests.
So you might be wondering, how does this actually affect a patient? Well, picture a free field hearing test. Sound comes out of a speaker, and it starts bouncing off every single surface in that room. This creates this incredibly complex web of standing waves, filling the whole space with invisible loud spots, the antinodes, and quiet spots, the nodes. Now, if a patient just moves their head a few inches, the intensity of the sound they're hearing could change dramatically, and that could lead to a totally inaccurate diagnosis.
Let's make this real with a clinical case. Imagine an audiologist sees that a patient is having a really tough time hearing sounds right around that 3,000 Hz range.
Then they look and see the patient's ear canal is blocked with wax. So what's the connection here? This table lays it out perfectly. In a normal ear canal, that quarter wave resonance gives you a natural boost right at 3000 Hertz. But when that canal is blocked, the resonance gets dampened or even wiped out completely. That natural built-in amplifier, it's been switched off. The patient isn't suddenly deaf at that frequency. They've just lost their biological hearing aid.
Okay, I think you've got the theory down pat, so let's put it to the test with one last little clinical puzzle.
All right, here's a situation. You're testing a patient, and the results are all over the place. They seem to hear way better or way worse just depending on where their chair is. What's the physical principle that could explain that inconsistency?
And the answer is standing waves. The patient is unknowingly being moved between those acoustic dead spots and hot spots in the room. And this, right here, is why having specialized acoustic treatment in audiology booths is so incredibly important. It's all about getting rid of these invisible architects so we can get a true, accurate reading of a person's hearing.
So there you have it. Standing waves are this fundamental piece of physics. They're a biological advantage inside our ears, but a huge clinical challenge we have to outsmart. Now that you know all about these acoustic traps, would you be interested in another explainer on how architects design entire concert halls to control these exact same phantom waves? Let us know down in the comments, and we'll catch you on the next one.